This is chapter 6, Comparative Statics and the Concept of Derivative. So the key word for this chapter is derivative, and we'll talk a lot about this term. So first is some background knowledge. So first thing we need to talk about is the rate of change and the derivative. So suppose we have a function that we're interested, that is y equals to fx. So sometimes we are interested in the change of y given the change of x. That means that when x changes from the value 1 to value 2, what is the change of y? Right? Sometimes we're interested in this kind of question. So we call the change of y the rate of change. And then we'll talk about the different quotient first. So we let delta x to represent the difference between x1 and x0. So this is called delta, this triangle here. It means change. Right? So delta x means when variable x changes from x0 to x1. So what's the difference between the two values? So the difference is called delta x. Okay. So when x changes from an initial value x0 to a new value, so x0 plus delta x. So this is just x1, right? This is just x1. But we write it as x0 plus delta x. So when x changes from x0 to x0 plus delta x, so the value of the function y equals to fx will also change from x0 to fx0 plus delta x, right? Because x changes from x0 to x1, right? So if you plug in the x to the function fx, so fx should also change from x0 to fx1, right? Because x changes, so fx will also change according to the value of x. So this is just fx0 plus delta x, right? So y changes from fx0 to fx0 plus delta x. So the change in y per unit of change in x is called the difference quotient. So it's written as this. So this function means the change of y. So delta y means the change of y when x changes. So if delta x is 1, for example, if delta x is just 1, so this is just a delta y, right? Because delta x is 1. And when delta x equals to 2, that means that x changes by 2 units, right? So delta y is, so this left-hand side becomes delta y divided by 2. So the left-hand side, delta y over delta x, means the average change of y given the unit of change in x, right? So because here we divided by 2, so it's the average. And for a given unit of x, what's the change of y? So this is just equal to, or we plug in the change of the function. So delta y is just fx1. So here delta y is fx1 minus fx0, right? Because x changes from x0 to x1, so delta y should also change from fx0 to fx1. So the difference is this. It's called delta y. And fx1 is just fx0 plus delta x, right? So they're equal. So delta y divided by delta x is just the right-hand side expression. So we can see that delta y over delta x, or the average change in y per unit of change in x, is a function of delta x. Is a function of x0 and delta x. So for the right-hand side, we've already know the function, right? F function. So if we know x0 and delta x, we can plug in those numbers and find the average change of y, or the left-hand side of the equation. So for example, if we have a function called 3x squared minus 4, so we can write the rate of change of y as this. So we suppose the x starts from x0, right? So fx0 is this one. Just plug in x0 to the function. And we suppose x changes from x0 to x0 plus delta x. Right, so x changes from x0 to x0 plus delta x. And so I plug in this into the equation. So this is the y value, right? y1, I call it y1, after the change of x. So this is y0. So the change of y is just 3 times the square minus 4, which is f x0 plus delta x. Right, so this thing, it is 1. And then minus fx0. Right, fx0 is just this thing divided by x. And then we rearrange the terms and we find that, okay, we can cancel the minus 4 and the plus 4 here. And we can cancel the 3x squared here and 3x squared here. So what is left is 3 times delta x squared plus 6x0 delta x divided by delta x. So this is just 6x0 plus 3 delta x. So this is the result. This means that when x changes from x0 to delta x, to x0 plus delta x, the average change of y is this thing. Right? The average change of y from x0 to x0 plus delta x is this thing. So suppose x0 equals to 3 and delta x equals to 4. So that means x changes from 3 to 7, right? Because x changes from x0 to x0 plus delta x. So delta x is a change of x starting from x0. So this just means that x starts from 3 and it changes to 7. Right? Suppose x changes from 3 to 7, then the average rate of change of y is given by this equation. Right? So this is 6 times x0 is 3, plus 3 times delta x is 4, so this is 30. So when x changes from 3 to 7, the average change of y is 30. Right? So this is what it means by the difference quotient here. Yeah, it's just we are interested in finding the rate of change of y given the change of x. So this is the answer here. So this means that on the average, as x changes from 3 to 7, the change in y is 30 units per unit change in y. It's per unit change in x. Right? Per unit change is because we divide delta y by delta x. So it's a average concept, right? So this is the average change of y because we divide it by the change of x. Okay, so first part is the difference quotient, which is the background of the derivative. So then let's talk about the derivative itself. So suppose x changes by a very, very small amount. So in this example, x changes from 3 to 7, right? It changes by 4 units. But suppose we're interested in a very, very small amount of change of x. So x just changes by very, very little. And what's the change of y? Right? So this is the concept of derivative. So when delta x is very, very small, we call that delta x approaches 0. And we write this as delta x, and there's an arrow here, and 0. This means that delta x approaches 0. Approaches means that delta x becomes a very, very small number. For example, 0.00000. A lot of zeros here and the 1. Right? So delta x is a very, very, very small number. But it's not 0 itself. So it just approaches 0. Right? It can be positive 0.0001 or negative 0.00001, but it can never be equal to 0. So this is the concept of approaching, right? So delta x is a very, very small number, but it's very, very close to 0. But there's always some deviation from 0. That means that delta x can never be exactly 0. But it can be a very, very small number that's very, very close to 0. So this is called delta x approaches 0. So if delta x approaches 0, then we can write the quotient as there's a limit sign here. So LAN called the limit. So this means that the limit of this quotient, delta y over delta x, when delta x approaches 0, is the limit of 6x0 plus 3 delta x, right? We use the example above. It's the same. We just plug in the quotient here. So the limit of this thing is just the limit of this thing, right? Because we've already derived this, right? These two things are equal. So we can plug in this equation here. And we can find that when delta x is a very, very small number and it's very close to 0, that means that 3 times delta x is also a very small number, right? Delta x is very small, so 3 times a very, very small number is still a small number. So this, the second term here, is very, very close to 0, although it's not 0, right? It can never be 0 itself, but it can be very, very close to 0. Whether or not it's positive or negative, it's very, very small and close to 0. So the second term here is something that's very, very small, right? So when delta x approaches 0, then this second term approaches 0 too. So 6x0 plus a very, very small number will be approaching 6x0, right? We cannot just cancel this out. Right? We cannot cancel this out. We cannot write 6x0 plus 3 delta x equals to 6x0. We can never write this equation because the delta x can never be 0 itself. But this thing can be a very, very small number, right, as I said. So this equation here is approaching 6x0. When delta x is smaller, this thing and the two things are becoming closer together. to each other. Sorry. So in this case, we say that the limit of this equation when delta x approaches 0 is 6x0. Although this equation can never be exactly 6x0, but as delta x approaches 0, so these two terms, the summation of these two terms will be very close to 6x0 here. So this is a concept of limit. And so this notation means the limit of something as delta x approaches 0. Right? Read as this. Okay. So if as delta x approaches 0, the limit of the difference quotient delta y over delta x exists. That limit is called the derivative of the function. So this is the definition of derivative. So first, the delta x has to be approaching 0. And the second, the limit of the difference quotient. Remember that the limit is defined as this, right? As well, when delta x equals to 0, then the terms here is approaching this term. So this is the idea of limit. So first, delta x should be approaching 0, and then the limit of the difference quotient, this one, should exist, right? So we'll see some of the cases when the derivative or when the limit of the quotient doesn't exist, right? We'll see some of the graphs later on, but here is just a basic concept here. Okay, so if these two conditions satisfied, then this kind of limit is called the derivative of the function. So derivative of a function, for example, derivative of function fx, means that when x changes by a very, very little amount, remember that delta x is very close to 0, right? So derivative means when x changes by a very, very little amount, what's the change of y? So that change of y is called the derivative, right? So if you draw a graph here, so this is y, this is x. So suppose x is here, right, x0. So suppose x changes by a very, very little amount. So suppose this change from x0 to x1, suppose the change delta x is very, very small, it's close to 0. Right, it's close to 0. So what's the change of y? So y changes from x0 to x1, right? So this difference is called the derivative. It's called the derivative of the function. Okay. But delta x has to be very close to 0. So the difference between the y's is called the derivative. And there are two ways to denote the derivative functions. So first one is we can write if the function we are interested is fx, then the derivative of the function is called f prime x. It's called f prime x. So this means the derivative. And second, we can use dy over dx to denote the derivative. Right? So delta y over delta x means x changes by a larger amount. Right? Delta x means x changes by a larger amount, but dx. So dx means the x changes by a very, very little amount. So that's a different notation and different meaning of the two notations here. So delta x means x changes by a larger amount, dx means x changes by a very, very little amount, a very small amount. So what's the change of y, right? So this is called derivative. And so we have the two notations, and then we can define the derivative of the function f equals to fx as, so this is derivative, and so this is the other way to write the derivative. So the 3 lines here means define, right? So it's defined to be. So this is also called defined to be. So the derivative of the function is defined to be limit delta x equals to 0, and then the quotient, right? Well, we can read this as the limit of delta y over delta x when delta x approaches 0. Yeah. So when delta x changes by a very, very small amount, the change of y is called the derivative. Okay, so for example here, suppose we have a function y equals to 3x squared minus 4. This is the same example as above. So dy divided by dx is 6x, right? Because delta y over delta x is 6x plus 3 delta x. 6x plus 3 delta x. So we don't write x0 here because we just suppose that you can choose any kind of x. Okay, so x can be chosen arbitrary. So x0 just all kind of x in a domain. Right? So there's no like specific x0. I mean any x. If you plug in any x, then the derivative is still the same. So in general, we write this as 6x plus 3 delta x. Right. So x, there's no like specific starting point, x0. So that means that x can start from anywhere. So that's 6x here. So this is a quotient, and the limit or the derivative of the function is 6x, because here, right? So this is just the definition of the derivative, right? It's the same. Here, the two equations are the same. It means that the limit of the quotient when delta x equals to 0. And we already know that this should be 6x, right? It should be 6x. Or we can also write that f prime x equals to 6x. So it means that the derivative of the function is 6x. So when x equals to 4, for example, then f prime x equals to 24. So this means that when x is 4 and x changes by a very, very small amount, then y will change by 24. And when x is 5, and so when x is 5 and the x changes by a very, very small amount, then the change of y is 30. So this is kind of like the sensitivity of y given a small change of x, right? So if y is more sensitive to the change of x, then when x changes by a little amount, it will change a lot, right? So this just means given a starting point of x, so here the 4 is a starting point, and here 5 is a starting point, right? And x changes by a very, very small amount, then the change of y is 24 and 30 respectively. So this is the concept of derivative. And then let's move on to the concept of limit. So we've already talked about something about limit. And here, to simplify, we write Q as the quotient here. V as the delta x. So the derivative, can be written as the limit of q when v approaches 0, right? So from now on, we'll talk about this equation, right? So first we talk about the left side limit and right side limit. What's the definition of this? So this limit of q when v approaches 0 is just a special case of the limit of q when v approaches n and n equals to 0, right? So n can be a arbitrary real number. So m is in R, right? So m is any kind of real number, right? R means real number. So this means it's in the set R. So n is a real number. And 0 is also a real number, right? So this is just a special case of this one. So when we say v approaches n, we can approach n either from values greater than n or from values less than n. So for example, here there's a line of the real value, right? If you write all the real values in a single line, so this is called R, and this is n. So for all the numbers in the left-hand side of n, so those numbers are smaller than n. And for all the numbers to the right of n, they are larger than n. So when we say that v approaches n, so they can be done by two ways. The first, v is smaller than n, but v is very, very close to n, right? So suppose n is 2. So v can be 1.999 all the way 9 here. So this number is smaller than 2, but it's very, very close to 2. So in this case, we say that v approaches n from the left side. And for the other case, v can be larger than n, but v is very, very close to n. So again, n is 2, so v can be 2.000, there are a lot of zeros here, and then 1, right? So v, of course, is larger than n, but it's very, very close to n. So one way for n is to approach from the left side, and the other way is to approach from the right side, right? So this is called left side and right side approaching. So the left side limit means when v approaches n from the left side. So that means that v is smaller than n, but is very close to n. And q is a function, right? Q is a function. Q approaches a finite number, L. Then L is called the left side limit of Q. And we can write this as the limit of Q when V approaches n from the left side. So here, there's a minus sign here. There's a minus sign here. So this means that V is smaller than n, but is very, very close to n. So we use the n minus to represent. And the right side limit means when V approaches n from the right side. So V is larger than n, but is very close to n. And Q approaches a finite number R. So R is called the right side limit of Q. And we can write the notation as this. So limit of Q when V approaches n plus. So n plus means V is larger than n, but V is very close to n, right? So here we can say that limit v approaches n minus q is just L, right? The number L. And the limit v approaches n plus q, this is R, right? So here we have the two limits, one from the left side and one from the right side. Right? And only when the two limits, L and R, have a common finite value, that means that L has to be equal to R. Right? That means that no matter how you approach the number n, from the left side or the right side, we have the same limit. L equals to R, right? We have the same limit. Then we say that the limit of Q exists. And we write that the limit of Q when V approaches N. So now we don't have to add a minus sign or plus sign here because the limit of Q exists, right? So we can just write V approaches N. So the limit of Q when V approaches N is just L and equals to R. Right. So there's a notation here. So there's a note here. The L must be a finite number. So that means that L cannot be positive infinite or negative infinite. If limit Q is positive infinite or minus infinite, then we say that Q has no limit because we don't consider the function approaches to infinity is a limit, right? Infinite. So infinite is not a number. Right? Infinite is not a number. So we cannot say that the limit of the function is infinite, right? So it has to be a finite number. It has to be a finite number, like 100 or 1000. No matter how big it is, it has to be a finite number. It cannot be infinite, right? It cannot be infinite. And infinite is not a number. It just means infinite. So we cannot have 2 times infinite or 1 over infinite, or we cannot compare infinite and infinite plus 1. Right? We cannot compare these two because infinite is just infinite. It means the number is very positive and it increases to a very, very large degree. So we cannot write it down, right? So this is called infinite. You can think of the infinite as the biggest number, but you can never write down the exact form or the exact form of the number. So in this case, we say that if the limit of the function is infinite, then there's actually no limit of the function, right? So L has to be a finite number. It cannot be like the function cannot be increasing forever or decreasing forever. It has to have a upper bound or lower bound. The upper bound and lower bound is just some finite number here, right? It cannot be like infinitely increasing or infinitely large or infinitely small. Right? So it has to be have a bound here, upper bound or lower bound for the function.